Okay, let's try this again. My last video had a render problem, so even after rendering it 3 times it didn't work. So I will start again. This is the installation of an aftermarket ECU into a Ducati 996 from the year 2000. I rebuilt this bike from a dozen boxes of bits and pieces, and it was starting and idling beautifully when I was finished, but it would never rev. It would sit and idle for as long as it needed to, but then as soon as the throttle was just touched, it would die. I checked everything I could, evaluated every sensor, calibrated the TPS, adjusted the carbon monoxide settings, swapped out all of the sensors, swapped out the wiring harness, swapped out the ECU, and nothing would fix the problem. Checked the timing multiple times. It was timed properly. It was then sent to a Ducati dealership, and they were unable to diagnose the problem. It was then sent to another Ducati workshop. They also were not able to diagnose the problem. So finally, after many, many years, almost 9-10 years since I finally handed this bike over to the owner, it's back. So we are doing the full ECU swap, which at the moment looks a little chaotic, but the engine is running. It starts up and it idles and it runs and it revs. Twisting the throttle actually revs it. It's working. So now we need to convert this mass of wires into an actual wiring harness. So I'm going to make 2 sections of this video. One is going to be describing the installation and just the basic parameters for the setup. And then we're going to talk about this, because after much consideration, I realize it's kind of overkill for this machine. So as a result, I have this. It is doesn't even tell you, but it's a 750. It's an Elite 750. And the reason I got that is because I have another plan for this 1500, talking to you, Mr. MV Augusta. Anyway, let's talk about the setup before we go into the unboxing of the 750. So I may have been a little unclear in my previous video. Maybe it's not such a bad thing that it didn't work. So here is the configuration. So in the Haltech configuration, we have engine configuration, engine capacity, 1 liter, piston, 4-stroke, 2-cylinder, naturally aspirated, maximum cranking RPM about 500. Makes sense so far. The odd fire configuration, cylinder 1 fires first. Cylinder 2 fires exactly 270 degrees later, so we can define that here. First to fire is 1, second is 2, after 270 degrees. So far, so good. That's the easy part. The next section is the trigger. This is the one that caused some confusion both for me and for the help desk at Haltech. So we're going to talk about trigger type. This one is using missing tooth with no home. So that's referring to a missing tooth on the cam gear instead of having just a cam trigger and then reading the crankshaft. That's what a lot of machines do, including that Husqvarna. It has a number of bumps on the crankshaft and a double bump. So that's what it refers to as the home. It doesn't use the camshaft. It has a single bump on the camshaft that it reads, so that it knows which part of the cycle it's on. So let's talk about that. Trigger signal location is on the cam. Number of teeth on the cam. So that's what this is related to here. That's what this is referring to. This is the cam drive sprocket, and I don't know if you can tell, but there's an indentation there where 2 teeth are further away than all the rest. this engine has a sensor in the cover that is positioned right here, right where that black mark is. That's actually top dead center, as we can see here, top dead center of cylinder 1. We've got 48 tooth minus 2, so there's 48 teeth, and then that is minus 2. That's how the engine and the ECU knows what to do. So let's take a quick look. The number that took me the longest to figure out was the TDC angle. Now, in the documentation, they actually call this the TDC angle, or offset angle, TDC offset angle, which is, in this case, 340 crank degrees. And it's important to remember the difference between crank degrees and cam degrees. So let's take a look at that. How do we figure the 340? Okay, so we're now at TDC, but we want to be at the reference point. So let's go straight to the reference point, and there it is. So at this point here, the computer detects that this is a reference point. It doesn't matter where that reference point, it just needs a reference point. As we all know, a bad reference point is better than no reference point. So the computer says, okay, I'm at reference point. Where do I need to trigger the first spark plug? We can calculate that by measuring the crank degrees of rotation between this reference point and TDC of cylinder 1 at compression. Because remember, there's TDC at compression and there's TDC at exhaust. We're only concerned about compression because we've told the computer to turn off all the ignition offsets. So it's only going to fire the spark when TDC is at 0. When piston number 1 is at TDC, which is 0 degrees. Okay, so again, we need to go from the reference point to TDC of cylinder 1. So we can look at this reference point, and we've now traveled 180 degrees. And we're coming up to 360, but we're not quite going to reach 360 because we can see that's where TDC at 1 is. And it turns out that it's about 20 degrees from a full circle of the crank shaft. It's actually only 170 degrees on the cam, but it's 340 at the crank, because remember, the crank rotates twice for every time the cam rotates once. And that's it. 340 degrees from the reference point to TDC of cylinder 1. TDC, cylinder 1 is right there. That's it. That was the most difficult value to arrive at. And then the rest follows on from there. So let's switch a few things on. So the fuel pump switches on, the tachometer cycles, check engine light is on, but that's for some cylinder fuel offsets that we can't process just yet. This is the fan relay. That's the ignition switch. That's the kill switch. That's the neutral lockout switch. And that is the starter output. The engine won't start if the kill switch is off. It also won't start if it's not in neutral. And when the fan source temperature reaches, I believe it's like 85 to 90 degrees, then the fan switches on and the fuel pump switches on whenever you switch the ignition on. We've got the tachometer output frequency mapped here because that's what I'm currently diagnosing. So we can actually look at what it is by using my fancy handy dandy multimeter. We'll set it to 4 millisecond increments, and then when I turn off the ignition, then we get 0 signal. When I turn on the ignition, the tachometer is supposed to sweep by getting that signal right there. Now let's look at the actual tachometer right here. Turn the ignition off, turn it back on, and we're getting only 6.5. readings, and it's doing that funky stepped motion. It's ironic that it goes to 6.5 because it's supposed to go to 13, and it's supposed to do it smoothly. So we may be a little low on the voltage, because when I switch it on, how low does the voltage go? 12.5. Yeah, 12.5. That doesn't explain it. Anyway, so that's what I'm currently diagnosing. But I think I'm going to stop at this point, and instead of diagnosing that problem, I'm going to install the other ECU. So this all works. The engine runs, all the functions work, but as I said, this really is overkill for 2 cylinders. The owner just doesn't need all of the data logging, the traction control, the suspension, potentiometer readings. It's got pit lane speed limiter. It's got everything. Yeah, as I said, traction control. It even has ABS built into this ECU, and it's just overkill. Of course, that's the key addition to this ECU right here. This engine in stock form doesn't have a knock sensor. Installing this knock sensor in it will do a lot to guarantee the health of this engine. Okay, so we could say that's end of part 1.